Welcome back to my channel. In this video we are going to talk about the SN2 reaction. We'll see the mechanism of the SN2 reaction, how the reaction comes to completion. We also see some factors that affect the SN2 reaction. So let us just kickstart with the reaction mechanism for this SN2 reaction. First, it is important to know that SN2 reaction takes place in a single step without an intermediate. This happens when the incoming nucleophile reacts with the substrate or the alkyl halide from a direction opposite the leaving group, and it displaces the leaving group once it comes in. Let me show you what I mean by that. Suppose we have this as our substrate. Yes, suppose we have this as our substrate, and like I said before, the incoming nucleophile should be in a direction opposite the leaving group. So this is our substrate and this is the leaving group, so it should be in a direction opposite it. So if we are using hydroxyl as our leaving group, it will attack from the back and kick off the leaving group. So when this takes place, there will be a partial formation of carbon hydroxyl bond and a partial formation of, or a partial breaking of, carbon bromine bond. So that takes us to the transition state of this reaction. So in this transition state of the reaction, there is a partial formation of, there is a partial formation of carbon hydroxyl bond and a partial breaking of carbon bromine bond, and it gives us a planar a planar structure or a planar diagram. So this is the transition state of the reaction, and when this comes to completion, this is what we see. This is what we see when this comes to completion. So when this reaction comes to completion, it will invert the configuration or the stereochemistry of this substrate. Suppose we want to assign priority and name this substrate. We say our lowest priority should be on bromine, second to the ethyl, and third to this methyl, and hydrogen to the fourth, as due how to assign R and S configuration. So we move our circular motion from 1 to 2 to 3 and see where our direction goes. Now it is going on clockwise. So since it is going clockwise, our configuration is supposed to be R. But since the bond pointing at us, the bond in the front, is hydrogen, which is the lowest priority, reverse will be the configuration. So it's not going to be R configuration, rather it will be S. So let's name the compound. The compound will be named S2-bromo butane. So that is the stereochemistry of this compound. But when the incoming nucleophile came in and kicked out the leaving group, this is what we get. Like I said before, it will invert the configuration. So let us see how that happens. So according to the rule of assigning RS configuration, this is taking 1, this is taking 2, this is taking 3, this is taking 4. Move our circular motion. We are going to the anti-clockwise direction, but because hydrogen is on the wedge, we reverse it. It's supposed to be S, but now it will be R. So the name of the stereochemistry of this compound is iron 2-butanol. So that is the stereochemistry of this. So this is how SN2 reaction proceeds. From the a back attack of the incoming nucleophile to kick off the leaving group, we get a completely formed carbon hydroxyl bond. That is how the SN2 reaction takes place. But then there are factors that affects the SN2 reaction. So let us just talk about some of the factors that affects SN2 reaction. Bulkiness of the group, or let me say steric hindrance. It has to do with bulkiness. If the compound is bulky, it slows down SN2 reaction. If the compound is not bulky, the reaction will be very fast. Let me show you what that means, what the bulkiness of the group means. Suppose we have a methyl bromide. Let me say methyl bromide. A methyl bromide. Yes, a methyl bromide. The reaction of this substrate will be fast. This is a fast reaction. The reaction of this substrate will be very fast compared to when we have, let me say, an ethyl bromide or a primary alkyl halide. Let me say, let us have a methyl group here. Let us have a methyl group here, the hydrogen bond pointing away. Here's a carbon, and we have this Br. Suppose we have this methyl group. What do you think? Which of them do you think will be more faster? Which of this compound do you think will be more faster? This group is more bulkier than this group. This is a primary alkyl halide, so it is more bulkier than this group. So the reaction will be more faster on this than this. Suppose we have a secondary alkyl halide also. The reaction of the primary alkyl halide will be faster than that of a secondary alkyl halide. Same happens to tertiary alkyl halide. So that is how steric hindrance affects the SN2 reaction. The more bulkier the group, the slower the reaction. The less bulkier the group, the faster the SN2 reaction. Now, another factor that affects the SN2 reaction is the nature of the nucleophile. Why did I say the nature of the nucleophile? Nucleophiles rather can be either positively charged or negatively charged. When you react a negatively charged nucleophile to a substrate, you get a neutral product. We react a negatively charged nucleophile with a substrate, you get a neutral product. Let me just show you that. Suppose this nucleophile is negatively charged. You react it with a substrate, okay, with your leaving group. The product you are getting will be positively charged. That is what that means. No, not positively charged, rather it will be neutral. Like I said before, neutral nucleophiles gives you positively charged products, while negatively charged nucleophile give you neutral products, and this is neutral. Let us see how that of neutral nucleophile looks like. This is a neutral nucleophile. When it attacks the substrate, you get a positively charged nucleophile. plus your leaving group. So that is how it happens. That is how it happens. So that is that for that. So that is one of yet another factor that affects the SN2 reaction. Like we all know, all nucleophiles, they attack from the back to displace the leaving group, but during this reaction some are faster than others. The more nucleophilicity, the faster the attack on the substrate. And we know that nucleophilicity depends on electron affinity, that is gain of electron. So when a nucleophile has much electron, when it is electron rich, the reaction of that nucleophile in a substrate will be more faster than that is electron deficient. So that is what that means. It is important to know that nucleophilicity increases going down a column of the periodic table. See what that means here. Suppose we have hydrogen sulfide. The hydrogen sulfide has more electron than hydroxyl. Let me write it this way, than this hydroxyl group. So reaction of this nucleophile with a substrate will be more faster than that of this hydroxyl group, and that of the hydroxyl group in turn will be more faster than that of an acetate, and the reaction of an acetate as a nucleophile will also be more faster than water. Water could also act as a nucleophile, you all know that. So it will be more faster than that of water. That of hydrogen sulfide will be faster than that of hydroxyl group. That of acetate will be more faster than that of water. So that is how nucleophilicity works in the SN2 reaction. It increases down the column of the periodic table. Yes, from what we can see here now, we see that negatively charged nucleophiles are more faster in SN2 reaction than neutral nucleophiles. Like we have water there is neutral, so the negatively charged nucleophiles are faster than neutral nucleophiles. Let us consider yet another factor that affects the SN2 reaction. That is the leaving group. We've seen the bulkiness of the group, also seen the nature of the nucleophile. Now we are looking at the leaving group. Leaving group are expelled in most SN2 reaction. We expect the best leaving groups to be those that best stabilize the negative charge. When leaving groups are expelled, they go out, they leave the carbon without any electron. They go out with their unshared electron. If they were pairing with the substrate with 2 pairs of electron, if they are pairing with 2 pairs, they will leave the carbon without the 2 pairs. They will collect the 2 pairs of electron from the carbon. So that is how the leaving groups works. So and the best leaving groups, they stabilize their negative charge. We all know that stability of an anion is related to its basicity. Therefore, we can say that the best leaving groups are the weakest bases. Consider, for example, tosylate. Tosylate is more reactive, is a much reactive leaving group than iodine. And iodine, because of the stability of its electron, is more reactive in turn than bromine. And bromine too, because it has a much unstable electron than that of chlorine, it will be more reactive than fluorine. Let me just show you that on the board. Let's see tosylate. tosylate, this is a leaving group, it is more reactive than iodine because its electrons are more stabilized than that of iodine, and iodine is more reactive than bromine because its electrons are more stabilized than that of bromine, and bromine in turn is more reactive than chlorine. Chlorine in turn also is more reactive than fluorine. So this is how the leaving groups works. This is how they affect the SN2 reaction. It depends on how much they stabilize their electron. If the stability of tosylate is greater than that of iodine, then tosylate is the best leaving group compared to iodine. So that is how the leaving group affects SN2 reaction. It is also important to know that alkyl fluoride, alcohols, esters and amines are not good leaving groups. Therefore, they do not undergo SN2 reaction. That is to say that solvents with alkyl bromide or alkyl fluoride, solvents with alcohols, solvents with esters and solvents with amines do not undergo SN2 reaction. If you use them, it will slow down the rate of SN2 reaction. So I hope these concepts help you in SN2 reaction or determining the step or the rate of SN2 reaction. So please, if you've not subscribed to the channel, please do well to subscribe. See you next week.